Hi everyone, I'm back with another video. This video is suitable or useful for people who are doing research on circularly polarized transmit arrays or reflect arrays. Um, in this channel, when I post videos on unit cells, simulations in ANSYS, I get a lot of questions about circularly polarized parameters like transmission coefficients, reflection coefficients, or axial ratio. So I thought I take or record a video that is more about fundamentals, because some of the questions I get, and basically I have to answer them with this video first, and then show you how you can simulate it, because there's you can't start a simulation without knowing what you're doing, okay, without knowing the fundamentals. So for example, one very good question I got was like, okay, you're simulating a unit cell and showing us like what is circularly polarized you know unit cell, but then as soon as you change the dimension of this unit cell, it's no longer a circularly polarized one. Why is that, right? So in this one, we have two concepts for circularly polarized unit cells, okay? Some of them are for polarizers. Polarizers are usually uniform arrays, meaning that all the unit cells are similar, and they are arranged in a finite array, square array, let's say, okay? They are uniform though. So as soon as you get one unit cell and then you make a copy of it, whatever dimension you need to, then you have a polarizer, okay? But for a transmit array or reflect array, which nicely this comments pointed out to, you don't have a uniform array of unit cells. The unit cells are going to be different because each of these unit cells at that position has to introduce a specific phase shift to the wave as it's coming, as it's inciting that unit cell, right? Okay, so I said all of this to say there is a distinct difference between how you would design a circularly polarized unit cell for a polarizer, and then how you would design it for a transmit array or a reflect array. These two are very similar. Reflect array is transmit array, okay? So let's go to fundamentals. I have a paper on, again, this is because I was really like, I was thinking about fundamentals of this too, because when I started my research, I'm like, okay, why is it that some transmit array in unit, reflectary, circularly polarized ones are in this way and some of them are that way, right? And then, so that led me to this research or to this work to show that there is a distinct difference between the working principles of these different types of transmitters. Okay, so I'm gonna go to the end to show you what you would see in literature on transmitters. Okay, so here I have two. Here, let me just draw this. I have two types of. I'm showing two types of transmitter. One is this one, and then the other. I chose like the worst color here, but one of them is looking like this, where you can see, the phase distribution across the transmitter because the size of the patches on the unit cells are changing. Okay, while the other one, it's kind of like you can see it, but it's not that obvious, right? And you can see, if you really zoom in, you can see that, let's see if I can zoom in. You can see that here we have unit cells that are rotated. So in this one, the dimensions of the patches or the metallic parts of the unit cell are changing on the top one. On the bottom one, the unit cells patches are rotating. That leads to this distinct difference between what I called in this paper phase delay and then the other one phase rotation. Because phase delay is like you're adding a phase to the incident wave, right? And then on the other one, you're doing the same thing, okay? You're adding a delay but you're doing that by rotating the wave, basically. By rotating it, you're adding this simulation. So when this happens, you're like, okay, when we have this difference, let me go back. Then there comes to the basic comes to this, that you can define two coordinate systems, one for each unit cell and then one for the whole array. For the unit cell, basically, it's best to define the coordinate system of the unit cell across its perpendicular to its metallic shape, right? Like this one. For example, I have a metallic shape, like a rectangular one here. Let me pick another color here. I chose black, but I don't know why it's not drawing black. Me and technology, guys. Like, this is not black. How is this? Oh, is it because of the... How? Okay, whatever. Okay, now it's moving. Okay, so in this one, if I have a rectangular patch on the unit cell, then it's best for me, simplifies my calculations, if I define the coordinate system of the unit cell along perpendicular to its shape, basically, right? So that's why x prime, y prime coordinate system. For that unit cell, it's looking like this with a 45-degree rotation compared to xy, which is our general coordinate system for the whole array. And then the neighboring unit cell, let's say the patch is horizontal, and then the x prime and y prime are in this direction. Why am I defining it like this? Because later, based on the rotation of the unit cell, okay, compared to the general coordinate system, I can define the reflection coefficient and the transmission coefficient of the circularly polarized waves compared to the linearly polarized wave across the unit cell. Okay, so for example, here, this is the reflection coefficient of a left-handed circularly polarized wave, LHCP. So if I excite this unit cell with an LHCP wave, how much would I get reflection coefficient in LHCP as well? Okay, and that one, you can define it like this, compared to the coordinate system of the unit cell itself. So, and then you can continue doing this. You can copy this, basically, use this, basically these formulas in your ANSYS HFSS simulation to basically, if you're exciting the unit cell with linearly polarized waves, to calculate the circularly polarized coefficients, reflection and transmission coefficients. So that's why I wanted to present these formulas, these equations, because sometimes I get a question, I'm like, how do you do that, right? I have another video that shows you how you can define your own equations in ANSYS HFSS. So you can represent the whole full matrix of, this guy, LHCP, RHCP reflection, and transmission coefficients by using these formulas, by relating them to the linear polarized wave. Okay? So now you're like, okay, well, how is this related to what you were talking about, the phase delay, phase rotation, changing, blah, 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 right? How is this related to it? Based on these formulas, I want to show you that we have two sets of unit cells. We have some unit cells that their transmission or reflection coefficients are equal. They are like squares, for example, like this one. So along the X and the Y, you have exactly the same transmission or reflection coefficients. And these unit cells, I'll show you that they can also be used for a circularly polarized transmit array and or reflect array. So when you're designing a circularly polarized TA or RA, you don't actually have to design a complicated unit cell. You can just go ahead and then, you know, design squared patches, stacks of square patches in your unit cell, and then still get a CP array out of it. How are we doing that? When you have a squared or something that is like symmetric, we call it symmetric along the X and Y axis of that unit cell, then you can say, okay, my TXX and gamma XX and YY are equal. And then since this is a symmetric one, by design, the cross polarized XYs are going to be 0. And if you put this in those formulas, this specific case, in the formulas of 2 to 9, what do you get? Now you learn that if you have this relationship, then if your unit cell defines a little bit of phase shift, a little bit of phase delay, compared to like a reference design, let's say, right? Compared to a reference design, you have another unit cell that has a little bit of phase shift. Still, Tx and Ty are equal. They're equal to 1 for a transmit array, let's say, and there is no phase difference between them. But this neighboring unit cell is slightly bigger than the other one. So you have the phase delay from one unit cell to another one. Then you can say that if you have that situation, then the cross polarizations in circularly polarized wave also going to be 0. And in the RHCP and RHCP to RHCP or LHCP to LHCP, you also have the same transmission coefficient that you have in the linear polarized ones. Weird, right? Because we thought like, oh, okay, whenever I'm converting from RHCP to LHCP, I'm supposed to have this 1 plus J or like a phase difference. No, you have to go back to the basics. Try this practice. Try to put these special case. Let's say you have a square. It's not a square. I don't know how. Let's say you have what do I mean? You have a square unit cell here, and then you have what is, let me draw another one. I was trying to do this on my iPad, that would be easier, but then stupid iPad doesn't record my face. So this is the second unit cell, also a square. This is one unit cell, this is another unit cell. Let's say this is our unit cell 1 or 0, our design is, and this is 2. So when I define the phase shift phi n, I'm defining it based on my reference to the original one. Okay, and then in these square ones, since both of them are a square, these formulas of 10 to 14 holds true, because along X and Y, you're going to have exactly the same transmission coefficient. There is no difference. And then you can say for each of these unit cells, the RR, the circularly polarized ones, would be exactly equal to the linear polarized ones. These are per unit cell, okay? Now, when you're designing the whole array, now all you need to do is follow the phase distribution that you need along the array plane, and then just choose the unit cells you would need. For example, for this one, I have a design here, okay? This is about 5 layers. L1 to L1 and L2 are the same on both sides. So basically, I'm adjusting 3 dimensions because these are squares. This is the type 1. The X and Y are equal. I'm choosing 3 different L's basically to get different phase shifts. But at the same time, I have to make sure that as I'm choosing L1 to L3, the transmission coefficient, if this is a transmit array, which it is, my transmission coefficient stays 1. So I have two conditions: choosing L1 to L3 in a way that I get different phase shifts, and then also I would get transmission coefficient almost at 1. So here you can see, for example, for normal incidence, I go from 0. I have about 63, I had to design 63 different cells to go cover from 0 to about less than 320 degrees. So I couldn't get from 0 to 360 degrees that you would usually need to get the full phase distribution. But I got from 0 to 320, which has less than 1 dB of loss, right? And then just look at the normal incidence ones. Forget the other ones. And then from 0 to 300, almost 20, with 63 combinations of L1 to L3, I could design this transmitter. Okay, so now when I design the array, and the array, it has a phase distribution formula, at each point it's a known formula, then I would say, like, okay, pick the closest phase shift you need, pick that unit cell from this 63 set, basically. That way, I would get my whole array. That eventually it will look like this. From 0 to 320, I have 63 degrees, 63 unit cells. And then when it gets to 330, I would go to wrap it to 10 degrees again, for example, and then choose that one. Okay, so this array that has more than 1,000 unit cells is combination of those 63 unit cells. Now here, I want to go back to another one. Now I want to cut this. This is the phase delay. You see, simple. You're designing a linearly polarized unit cell as usual. The only thing you care about at the end is that I get the 0 to 360 degree. At the end, you would care about just putting the right phase difference. And you're like, how is this a circularly polarized transmit array? I would say it's a circularly polarized transmit array if you excite it with a circularly polarized incident wave. Because if you have this, for example, this is almost like a Y direction horn, right? If you design it with circularly polarized ones, then because it responds exactly the same for X and Y, a circularly polarized one would excite it with an EX and EY that are 90-degree difference. So if you have 90 degrees difference before the transmit array, you would have the exact 90-degree difference after the transmit array, because the transmit array has no filtering effect. It would only apply phase difference. And you can do that here. For example, I didn't want to simulate a circularly polarized horn. So what I did was I imported a linearly polarized one. I found one CAD model, and then I rotated it. So I had one simulation with Y direction and one simulation with X direction. And then I got the RHCP, for example, result at the end by doing a post-processing based on this formula. Okay, for X and Y, you would get a theta in the far field and a phi component, and then you can process it like this. So here it is for you, another formula. So you don't have to go and simulate a complicated circularly polarized wave. Horn antenna. Now let's go to the second one. Okay, so this is what I covered so far. This is the case I covered so far, phase delay. This is the simple design of the unit cell. Okay, and at this point, I'm going to stop. I'm going to let you digest the phase delay. Oh, why am I did it wrong. Phase delay 1 here. Phase delay, it says if you have a RHCP feed, you are exciting it with an RHCP, mainly RHCP wave, right? And you have some cross polarization because no feed is ideal. You have some LHCP. And because you have a phase difference across the transmitter plane, your RHCP and LHCP, both of them are going to get directed that way based on your transmission coefficients. And you have a reflection coefficient because things are not ideal because of oblique incidence, let's say. Then you would have a reflection coefficient back lobe exactly on the mirror side. Because of the Snell's law, you would have exactly the same on the other side. Okay, so no filtering effect. Again, just applying phase shift the same way you would do it to a linear polarized one. Now, I'm going to stop here and then record another video for the second part where I would cover the phase rotation transmitter.